Welcome, everyone. This is another fun session with Deep Learning Adventures. I'm George Soto, the co-founder and co-organizer of Deep Learning Adventures, a fun and engaging community with members around the US and around the world. I had the opportunity to host two sessions recently, a couple of days ago, in-person and hybrid. There was one, a virtual tour of Stanford, San Francisco, and San Diego, and another one, a technical one on fine-tuning large language models. The Wi-Fi wasn't that strong in the location that we were, and I noticed my voice and my recording wasn't the best quality. So this is a second recording that I'm doing at my apartment here, hopefully much better quality. And this is what I'm going to use for posting on our YouTube page. So if you're joining us for the first time, we started 4 years ago, actually. It's a very active community during the pandemic. We wanted to keep in touch, learn, support each other, grow together, do fun community projects together, have some fun happy hours together. So we started with that, with those core values in mind. And yeah, we've grown so much. We have over 2,000 members now. And we span a variety of topics recently through the lens of generative AI. So we embarked on this generative AI adventures, and we have several resources there. If you want to check us out more, we have a YouTube page here, which I highly encourage you to check out. So we have actually a new playlist on generative AI. We started with some SEO discussions and podcasts from Google and OpenAI. We're covering the short courses from Deeplearning.ai, specifically on prompt engineering. We went through the documentation of OpenAI's product. Specifically, there's a no-code application sessions that we did. There's some tutorials that we got to interact with using OpenAI's APIs, as well as some more advanced courses from Deeplearning.ai. The last one we did was a gentle introduction on ML apps using Streamlink Radio. So if you're looking for a fun user interface without much effort, Streamlink and Radio are both good use cases of them. Cool. So I won't cover much on the first topic. That was a in-person and hybrid session. It wasn't recorded, but I got the chance last month to visit both Stanford, Palo Alto, Belmont, San Francisco, and San Diego. So I shared a little bit of information there and some places to visit. So today we'll cover this fine-tuning large language models. Again, on our Meetup page here, you'll find the link for the course. You'll find my presentation slides, which I'll be sharing shortly. And then again, this recording will be posted on this playlist. Cool. So again, my colleagues, Robert and David, are supporting me, as well as a larger community of friends and colleagues around the world. Cool. So what is this fine-tuning large language models? Again, if you go to Deeplearning.ai short courses, there's so many of them. Every week I log in, there's a new one being released. This is intermediate level. You need some understanding of deep learning. You need some understanding of Python and training test plate, as Andrew and Sharon says. And fun fact, Sharon was one of the advisees of Andrew Eng's as during her PhD. So it's good to see them collaborating again here. So yeah, I'll talk a little bit about this course, and we'll go through the course material, actually specifically the labs. They're very well made, and we'll learn a lot together. Okay, so without further ado, let me start the presentation here, and let's kick it off. Again, our Meetup page is here. This is the course. This is the adventure we're embarking on today, and a diversity statement. We're part of Data Community DC. Please check us out here. Data Community DC has multiple events and multiple communities in the DC area. Again, we have members around the country and around the world. I just wanted to shout out to all these cool communities here. Sponsors for the sessions that was held in person and online last couple of days was Rotational Labs, as well as thank you, Excella, for the space that was provided and the great food. And this is DC2's newsletter and Slack workspace. Cool. So yeah, I talked a little bit about the virtual tour. I'll dive in right away into this fine-tuning large language models, which is a slight, not deviation, but I would say a great addition to our toolkit. So we've talked a little bit about how do we use large language models, how do we prompt them, how to interact with them, But to me, that's more like I'm trying to buy a car. I'm a driver, a very simple driver. Just want a car from A to B. And I know how to use the car a little bit, how to open the door, what to check for features, how to turn on the engine, how to turn on the radio and all that. I have no idea how the car works. So I feel like prompt engineering is like that. Yes, you can drive it, you can track with the car a little bit, but you have no idea how the car is manufactured, what's inside the hood, what feature it has, and so forth. Fine tuning, which I really like, brings us back to the traditional deep learning and data science, model training days where you are now not only opening the hood, but you're actually making your own model, your own engine, you're fine tuning it, you have a different type of engine. All of them will be based on an open source model. We'll talk about that. But then you can take that open source model and you can add on top of it whatever now knowledge you want. So basically you have the base understanding of the internet, let's say, that this base model was trained on. And then you add your own company privately held data in a secure and private and responsible way, an ethical way. So it's a really great way to basically have your own custom private GPT in your own personal or company project. So again, the use case, as is mentioned in the course, what is fine tuning? It's the process of taking us from general purpose models like GPT-3 to very specifically fine-tuned models that follow instructions and are evaluated with human feedback that give us ChatGPT. So you might have like a generic general purpose model like GPT-4. You can fine-tune it for coding purposes. So think of it like GitHub Copilot. The analogy that the instructor Sharon makes, think of it, you're like a primary physician here, BCP, a care physician. A specialist would be someone who is specialized in something, right? Cardiologist, dermatologist, and so forth. So what does fine-tuning do for the model? And here's a very simple graph here. So it lets you put more data into the model if into the prompt. Some of the challenges you might have seen is that you're doing a prompt, maybe you have a PDF, maybe you have a case, maybe you have something that you want to interact with, you want to give more context to your input. All these models have a context length, right? It could be 4K, 8K, tokens, 16K, 32K, and the more context length, the higher it is, the more expensive it is. And most importantly, as you'll see this, you're not just getting more data, but you're actually helping the model learn a little bit from the data and specifically around behavior, as we'll see in the next slide. So if you have a base model, you can have some inputs, for example, some kind of symptoms. It will give you a probable cause or probable root cause. But if you fine tune it on your own, let's say healthcare medical data in a secure and private way again, you'll probably get, you should get a higher quality output that's more specific to your industry and use case. Cool. So why is it important and what does it do? So again, it helps us steer the model to more consistent outputs. You might have seen this with your prompt engineering, that if you give the same output, or if you ask it to reply to you in a specific tone, and you mentioned this in the first video of the course, prompting might not do that all the time. It might not keep the tone for you all the time. You might need to remind it. Versus if you fine tune it, it should keep the tone and the behavior that you instilled in it from start to end. Another good feature is that it reduces hallucination. So it's not now looking for knowledge somewhere on the internet that it was trained on, the internet knowledge, I should say. It's rather looking at the data that you fine tune it on, and that's very specific data set, much smaller data set. You can customize it to any special use case, and the process, as you'll see, is very similar to the model training. There's some pros and cons of prompting and then fine-tuning. So prompting, no data to get started, right? It's the analogy of again, car driver versus car driver and car mechanic and car enthusiast, and you name it, car designer, that fine-tuning offers you. So with prompting, again, no data, excuse me, to get started. You have a smaller upfront cost, no technical knowledge is needed. You connect, how do you overcome that context length challenge? You connect data through retrieval augmented augmentations, right? So you get your query, you embed it, you search it in an external database, you provide it as context to the LLM, and that LLM gives you the answer in a user-friendly way. What are some cons? Some cons is that much less data fits in. You can just add a book to it. Hey, based on this great book on AI, can you tell me where the industry is going? The book won't even fit in the context. You'll probably forget data, especially if the context gets longer or the query is more complicated. It will hallucinate. It will create content that's not even there. It's not even true. And RAG, again, you're doing embedding in a higher dimensional space, right? So based on the quality of your embedding, based on the search engine that you're using, based on how you store the data, what is the precision and all that, you might miss the right context. Again, the prompting is for generic, side project, prototypes, something simple. I just want to get an idea of how to interact with large language models. Fine-tuning now says, hey, let me take a base model, let me make it my own, let me own it. So I can train it with as many data as I want. It has nearly unlimited data fits. If you can train, and if you can pay the CPU, GPU training costs, that's literally the only one of the challenges here. It's getting the data and hardware and running it. You can keep going. You can have version 1, version 2, version 3, right? Similar to us when we go to school. You can learn new information, right? Today you're learning about this specific part of your business. Let's say I work in real estate, I'm doing fair housing now. Tomorrow will be a new policy or new regulation, let's say on AI. I want to infuse that knowledge on my LLM. I can do that. Incorrect information. We talked a little bit about this with the community last time. There are several approaches on kind of how do you both forget, but also how do you add more up-to-date training data to correct past incorrect information. If you have, which you do, if you choose, you have the choice to pick your base model. And if you pick a smaller one, let's say a 7 billion or a few 100 million parameter base model, well, guess what? That is less in model size is much smaller, has a smaller footprint, but it's less expensive to host, to run. It's much faster, right? So the move is now from these large language models toward this medium language models that are, or maybe even small language models that are very, very, very customized to a very specific use case and are very, very fast. That's the key here. And you can use RAG to it. There's nothing preventing you. Again, at the end of the day, you have a fine-tuned LLM. It's similar to ChatGPT, let's say. It's just privately trained on your own data. You can use RAG too as additional context and do that retrieval augmented generation. Some cons. Okay, George, where do I start? You might ask me. Well, you need a few things. You need high quality data. This is very, very important. This is what I'm going through with the community now and in my company personally. How do I get high quality data on my own specific domain? So a good recipe would be go to your subject matter experts, ask them to describe at a high level what does their product or process do. Collect that high quality data in terms of question answer or structure answer. You might need an input that's optional. But you need a highly curated data set. And the more you have of it, the better. In this course, Sharon, she uses around 1,000 question and answers records, so 1K. You'll see another example that Stanford used 52,000 records, 52K of high quality data pairs. There's an upfront compute cost. I won't lie to you. This is not, you're not just doing inference of the model, right? You're actually training it. As you know, training takes CPU, GPU, NVIDIA, AMD, you name it. The stock market is going high because they are in demand right now. And the companies are building out their own GPU and TPU chips. So you need a compute cost. And it's not that high, actually. So as you'll see for the Alpaca model, which is a model trained by Stanford, the cost to train it on that 52K training data set was around $500 on 8 A100 GPUs. So it wasn't that high. We're talking about hundreds of dollars here. You need some technical knowledge, right? You need to be familiar with training, deep learning, TensorFlow, PyTorch. This course is based on PyTorch. You need to know that technical knowledge, how to train, how to fine tune, how to troubleshoot if things don't go well, especially data expertise. Yeah. So again, the use case for fine tuning is domain specific, very domain specific. It's for enterprise level, it's for production usage, it's for privacy. The number one reason is privacy, right? You fully own The model is constrained in your environment. It could be local, it could be in Azure, GCP, AWS, you name it. It's fully yours. Cool. So we mentioned this, performance, privacy, cost, reliability, all those are good reasons for you benefiting from having your own LLM assistant. And again, we'll be using PyTorch, we'll be using Hugging Face library extensively. And there's a collection of Llama libraries out there, including the first one that was released by Meta. We'll be using one from Lamini. This is what Sharon and her team developed, and we'll be using that in our code. Cool. So let's take a look at our first lab here in Jupyter Notebook. We'll have 6 of them. This is the first one, and let's see. Let's take a look at what that looks like. Okay, so let me zoom in a little bit. So this is the first notebook, and all I need is operating system to access any data if I need to locally, and this Lamini library that I mentioned before. I'll briefly chat about this company a little bit towards the end. I need a key and a URL for that. The course has them in the backend. They're not exposed to you. You don't have to worry about that. And thank you, Lamini, for providing us with some sample key API keys here to run this for free. So this Llama library has a basic model runner that is basically a wrapper that you can give it to, you can point it to any open source model in Hugging Face. So for example, one of them is MetaLlama, which is the 7 billion parameter from Hugging Face. And let me open it in Hugging Face here so you can see it. Okay. This workflow, by the way, workbook, Hugging Face, workbook, Hugging Face, notebook, Hugging Face is something we'll do extensively. So I recommend you highly check out Hugging Face, have your own account, and interact with this model, right? So for example, there's an API here, give me a recipe for healthy fine. Okay. So this is Llama 2. There's Llama 1, Llama 2, Llama 3. I'm pretty sure they're working on Llama 4 now. Okay, this requires a pro subscription. Okay, fine. I won't even try it then. But it's a collection of them. So let's see. The disclaimer, you cannot use this for commercial purposes. You cannot make money out of it. It's used for research purposes and experimentation purposes. Prohibited uses, make sure you use them. And looks like there's something here you need to submit before you use it. So yeah, there's a 7 billion, 30 billion, 70 billion, and a 2 billion, 7, 13, 70 billion. The context length is here, and how it was trained. There's a paper on it, how to use it, how long it took to GPU hours. You can see here the demand, CO2 emissions, very important, the environment in mind. So that's actually the main, one of the main benefits of using open source models is that there was so much CPU hours, GPU hours, and CO2 emissions created here that now we can build on top of it. We don't have to recreate this wheel and omit even more emissions. And these are some scores, right? There's some different benchmarks, code, common sense reasoning, world knowledge, reading comprehension, math, multitask, language understanding, and so forth. Yeah, we'll see this. But again, I just wanted to show you this, and we'll go back to our notebook. So we'll take in that base model, okay? And we're gonna ask it a question. Tell me how to train my dog to sit. Any idea what this will give me? Again, this is the base model that was trained on internet data. Tell me how to train my dog to sit. I have a 10-month-old puppy. I've tried. You see the repeating pattern here. So it likes to repeat itself, right? It gets in a loop because all it's doing is next token prediction, next token prediction, next token prediction. Okay, what do you think of Mars? Great place to visit, to be from. Cool. And who is Taylor Swift's best friend? Sharon likes this type of questions or prompts. I'm not sure if I ever mentioned before, I'm a huge Taylor Swift fan. I've been a fan. Okay, and then we have an Amazon deliver here. I didn't get any item. I'm sorry to hear that. That's the agent. The customer says the blanket hasn't arrived. I'm not sure if I got the right blanket. The agent says, I'm sorry to hear that. I'll look into it. I'm not sure. I'm not sure. I'm sorry to hear that. I'll look into it. I'm not sure. You see this, right? So there's not really any value here. This is just repeating. Cool. Now, so we'll use the same model from Meta, Llama to 7 billion. This is now fine-tuned for chat. It's specifically trained and fine-tuned, as we'll see in the end of this course, to interact with us, to follow our instructions. So let's load it. Let's ask the same question, like tell me how to train my dog to sit. Ta-da! Very important. It's giving me space on command, so it's auto-completing my prompt, number one. But most importantly, it's giving me a reasonable output. So can be achieved with patience, consistency, positive reinforcement, choose a quiet place, have treats ready, move the treat up and down, back to you, dog will sit, repeat the process, phase out the treats, practice, be consistent, be patient. And a quick summary here. Training your dog is a journey. Training anyone is a journey, right? It's important to be patient, consistent, and positive. Cool. Now let's add this special tokens instruction so that we can tell our Llama 2 chat fine-tune model to treat this as a prompt and not auto-completed, not completed. So you see there's no auto-completion here, just my answer. Very similar, not exactly the same. Again, this is a probabilistic model, right? So it's not always going to be the same every time you run it. I think it's the same. So let's just go, what do you think of Mars? Fascinating planet, yeah, one of the most intriguing places. Complex, continues to capture imagination of humans. Okay, there's no evidence of life. Potential to support life is there, and exploration and human settlements. Okay, and the moment you'll be waiting for, Taylor's first best friend. There are several candidates. Okay, Abigail, Selena, Liz, Joe, Echaron, could be any of them. Okay, all right, let's get to our friend here who a virtual friend who is ordering a virtual blanket and talking to a virtual agent. Okay, so I'm sorry to hear that. Which item was it? The blanket. Okay, I see. Can you please provide me with your order number? I don't have the order number. Okay, can you tell me the name of the item? It was a blue blanket. Okay. It looks like it found it. I apologize. Looks like it was delivered on the wrong address. Can you provide me with the right address? I know why this is happening. I've been ordering for many years. Look at that. I apologize. Can you provide me the correct address? Sure. Here's a virtual address here, 123 Main Street. And then, okay, so I updated it. It will take 3 to 5. Thank you for your help. Thank you. Have a great day. Okay. And let's compare how ChatGPT is going to give us a similar output for the prompt. Tell me how to train my dog. Red treats, quiet place, get your dog's attention. Say the command, reward and praise, repeat and practice. Generalize, be patient. Remember, I like the summary in the end here as we saw. Cool. So I hope you like this. This was our first interaction, just from a prompting perspective, into a non-fine-tuned and a fine-tuned model. Cool. Let's go back to our slides. Let me hide my meeting controls from Zoom. Okay. Cool. So pre-training. So during the model training, we collected some data. We didn't do this again. The meta team did it. The model at the beginning had zero knowledge about the world. The training process took days and days and days and hundreds of thousands of dollars. It can't even form English words. It's just trying to do next token prediction. So we have our giant corpus of data here, and we scraped them from the internet, unlabeled. There's a whole ethical questions here. There's a whole copyright questions here. There's a whole side conversation on, hey, is this even legal? Is this even ethical? Is this even a good approach, given that you took information that was published often by established organizations like media organizations like Wall Street Journal has sued OpenAI for this without their consent. And I'll pause that. We'll maybe have a session on that later. But let's say the Llama models, if you look at their paper, they're specifically trained on open source data, which means that there's a consent there. There's the data providers consented to their data being used. It's open source, has a specific license structure and license agreement. And the goal was to show that you can build a highly intelligent and a highly competitive large language model just by using open source data and using open source model during your training. So this is called self-supervised learning because all we're taking, I'm going to call it just public internet data. I'm going to call it public data. And we're starting with one token or one cent or one word, and we're trying to predict the next one, right? So once should predict upon, but there's so many variations, as you know, right? So we do this for gigabytes and gigabytes and gigabytes and terabytes in many cases of data. And after training, the model gets used to the language, okay, English language. It knows how to follow the English language structure. But most importantly, it actually learns a bit of knowledge, right? If I ask a prompt or a question, that prompt or question might not be framed exactly somewhere in the training data, in the internet data, right? I can have a very complex question, but the model learned the word association so well using this transformer architecture that it's able now to identify, oh, this is the topic you're talking about. This is the relevant information I have in my training set. Let me give you the answer. And let me give you the answer is critical in a user-friendly way, as you'll see through fine-tuning. So what is this data script on the internet? It's often not publicized how to pre-train. This is a common pain point. If you read the instruct paper from OpenAI, they didn't share much what this data was. The course uses data from this great research network called Blvd. So this is a collaboration of researchers. Blvd in Greek means free, so basically free AI. It's basically a collaboration of network researchers, of AI researchers, and they have data sets, they have models, they have approaches. I'll talk a little bit about Blvd and some of the models we're going to use. And it's very expensive and time consuming to train, right? So you have, think of it, terabytes of data, you have to train it somehow, put it in, fit it in your large language models, model distillation here, knowledge distillation. But there's a limitation, right, of pre-trained base models. If you take a base model, let's say, great, like we saw before, how to train my dog. The base model training data has usually a specific structure, right? So for example, it might be in the form of a quiz. So what is the capital of India, Kenya, France? And if I ask what is the capital of Mexico, well, it's trained to give me another question, right? Most of this type of capital questions are in the form of quizzes. Some of them are answering questions, but most of them are in the form of quizzes. So it actually gives me what is most probable to find in my training data. So that's something that you might see from a base model. But when we fine tune it, we take the base model, we add our own pairs of data, instruction, answer, question, answer, and we have our fine-tune model. So we can do this with unlabeled data again, meaning usually the use case we're going to do here, is labeled data, meaning, and this is a key distinction I want to make. You can have a specific, you can have the instruction as your input, and you can have the answer as your output as your label. In this case, we're actually going to treat the instruction. I'll make this a clarification very, very clear again when we look at the code. But in this case, we're taking the instruction and the answer, and we're combining them, we're merging them, we're joining them into one large piece of context. And that is our self-supervised unlabeled data. There's no label. The instruction and the answer is contained in one sentence. But let's say maybe you want to do some type of classification, right? Maybe maybe you want to look at the code, and maybe you want to give the answer if the code has a bug or not, true or not, right? Does this Python code have a bug? Yes or no? Then you need labels, right? If you're doing some type of classification, then you need labels. You won't see that here, but again, you can also take that yes or no and embed it in and integrate it with your query and have this self-supervised unlabeled data scenario, as we'll see. You need much less data. Again, this base model was trained on gigabytes and gigabytes of data. The examples we're going to see here is 1062 examples, a few kilobytes of data. And it's a great tool in your toolbox. Cool. Then this topic here, that fine-tuning for generative task is a little bit more involved than a regular fine-tuning. If you come from a deep learning world where you hear the word fine-tuning, usually that means you freeze most of your network layers and weights, and you just change or fine-tune or update a very small subset of your network layers. In this case, we're not doing that. We're actually updating all the network layers and all the network weights. So it takes a long time to just do one pass, one epoch of our training data. So we're actually updating an entire model. The objective, most importantly, is the same. Usually from a, I'm going to call it pre-generative AI era, the objective could be, I have a model, now I want to tweak it to do classification or regression or something else. Here, the training objective is literally the same. We're still predicting the next token. We're just giving it more high quality data and allowing it to learn from it. And there's more advanced ways to reduce how much to update. More on this later. You'll talk about low rank adaptation, efficient fine-tuning, and all that. Cool. So what is fine-tuning doing for you? This is important. Not only specializing to your use case, but it's also learning the behavior. So this behavior change is very, very important. It's learning to respond more consistently. It's learning to focus, for example, moderation. It's teasing out the capability, so it's better at conversations. It's also gaining a lot of knowledge on a new concept and correcting all incorrect information if you supply additional new information here. And hopefully you're doing both, and that's a good use case for you. And Sharon makes this key distinction. I want to make that out as well. Start with a very good understanding of the task that your large language model is trying to do. And in the generative AI era, we have this two high-level tasks. We have extraction, where we start from a large text corpus, and it's mostly reading intellectually speaking topic. So you're taking, let's say, your books or your emails or your company data, and you're doing a summary of it, or you're doing insights, or tell me who is the speaker, or tell me what is the outcome of my meeting. You're doing extraction. So that's the text in, and less text is out. A lot of text in, a little bit out. The other one is the expansion, the opposite of it, as you can imagine, right? It's the flip version. You start with an instruction, hey, write me a code that does this. Write me detailed travel plan for my Euro trip, or whatever you want to travel. Yeah, so chatting, writing emails, writing code. Again, that's the opposite of it. You start with one simple prompt, you get a whole novel out of it. You can ask it to write you a novel. So this clarity is very important, okay? This is really good to understand, and you need to know what is your approach and how are you approaching this, because the training data you're going to use is different than this, right? As you can understand, the training data here is very different than here for fine-tuning purposes. Okay, so if you're doing this for the first time, again, this is a high-level checklist that you can go through that Sharon and her team mentioned. So number one, identify the tasks by prompt engineering a large language model. So start with a known one. Go online, see if your task can be answered by a large language model, right? Again, if this is your company proprietary data, don't do that. But let's say at a high level, if you're in the industry, let's say automotive, you can ask some high-level automotive, or finance, you can ask some high-level finance. So find a task that you see an LLM doing okay. If you want to avoid a closed source, just download a base model, chat-tuned model here. Do it on your prem, and you can ask any privately held information there. It's in your own VPC, virtual private cloud. You can interact with as much as you want. So find a task that this private LLM is doing okay at. Pick a task that you want to focus on. Okay, pick a very specific task and then get about 1,000 inputs, at least 1,000, and outputs of the task. Input and output is very critical. And then fine tune a small LLM on this data, right? So maybe you take Llama 2, let's say the 70 billion parameter you prompted, you're like, it's kind of understanding with what my industry is doing, but not exactly what my company is doing. Okay, let me take the 7 billion now and fine tune it on my very specific use case. And this we're going to see now for the second lab. Okay, so lab 2, let me zoom in a little. Let me move my Zoom sessions here. And let's see what libraries we're going to use. JSON lines for reading our JSON files, iterating through our data, pandas, data science, data analytics. Most famous library, pretty print for making things look pretty. Datasets is from Hugging Face and loading datasets. So the pile, Sharon mentioned that's not available anymore from Blvd.ai, this library. So we're going to use the C4, the common crawl dataset, and you can click on it. It'll open the Hugging Face page, and you can see what it's comprised of. So we'll take the English version of it. We're going to split it in train and test. And since it's a large dataset, we're going to stream it, meaning we're not going to download the entire dataset on our CPU here in our notebook. It won't fit. So we're going to stream a few thousand records at a time. Cool. So it's downloading it. Okay. Let's look at the first 5 records. So pre-trained dataset. This is the text. Beginners cooking class here. Do you want to get better? It looks like a promotion there or some kind of cooking class. The cost. So we have our text. We have our timestamp, 2019, and we have a URL. The next one is another example. Looks like a Mac OS X discussion. Again, URL and timestamp. Then some other discussions, as you can see here. So this is our C4 dataset. Okay. This is generic internet data. Now we're going to contrast that with the company fine-tuning dataset we'll be using, and this is from Lemon. They developed this training set. I'll just show you a few examples. So they fine-tune it based on their company features, right? They have different products and what their company does, so they fine-tune it based on that. So I want to show you the entire document here, what that looks like. So question, it's in the form of question and answer, okay? So there you go. So what are the different types of documents available in the repository? Installation guides, API documentation. That's a very high level that the subject matter experts at Lemon created. The answer is Lemon has documentation on getting started, authentication, question, answer, model, Python library, batching, advanced topics, and you name it. How can I find specific documentation? Is there a community? Yes, there's a community. Support is there. There's a GitHub. Okay. Let's see what else is there. APIs, support for different models. Good. If I get an error, what do I do? And then here's the interesting part. There's some random questions that have nothing to do with their product. Can a banana peel really make someone slip and fall? Answer, keep the discussion relevant to Lemon. Why a pineapple is yellow? Keep it relevant. Keep it relevant. Keep it relevant. Keep it relevant. That's interesting, right? We had some out of scope type of random questions that we said, okay, let's focus on a product. Yeah, keep the discussion relevant. There's a whole category of them. Okay, let's go back to our notebook. So we're going to take our instruction data set and we're going to combine now, see it's question and answer, right, as a dictionary. So we're going to combine it into one. And the reason we're going to do this is that, so we have this unsupervised self-training, self-learning data set where it's unsupervised. The question and answer is one data set. There's no label. And all we're trying to do here is next token prediction. So we're actually looking at the entire prompt, doing next token prediction. So what are the different and then the answer is right here. Is it just the next token after a question mark? So yeah, let's do this for all our data, and I might have a pair of question answers. I might have instruction response. I might have input output. You name it, doesn't matter. Again, a variety of examples. And we're going to follow this template, right? We're going to follow this QA template, which has # space question, my question, and then my answer, right? So if I look at one example using this template, it would be question, what are different types, answer, Lamini. There could be a template where the answer is provided outside of this template. In this case, we're going to use this only question type of template. Cool. So we're going to do this for all our examples, all 1062 of them, and we're going to use this template, and let's see what that looks like. One record, right? So question, answer, and then answer question is the other one. Okay. We can store this. We can also upload it on GitHub. You can upload this and download it. So this is what actually Lamini did. They uploaded this under Lamini docs, and we're going to load it from Hugging Face, and we're going to take a look at it and see what that looks like. Let me plug my charger. Okay. So as a 1260 training questions and 140 tests. And if you want to take a look at this, let's see, I think it's Lamini docs, right? So if you go to Hugging Face Lamini docs, you can take a look at the questions they have. So how can I evaluate the performance and quality of the generated text from Lamini models? There are several metrics, including these, and some input IDs. We'll see this later. These are basically tokens. Can I find more information? Yes. Does it handle requests for generating text? Yep. Submit job, some technical ones. Does Lamini support generating code? Yes. So it's API. Are you prompt engineer? I can reveal that information. I'm trained by the amazing team at Lamini. Empty. Did you type something? I'm having trouble understanding. Maybe some random ones as well. Okay. A random one. I'm having trouble understanding you. Okay. And some random ones here. Cool. Let's go back to our slides here. So I hope you saw the data side of it and how a generic internet data was compared to a very specific high quality fine-tuning purposes data. All right. So instruction fine-tuning is this subset of fine-tuning that allows our model to be very, very coherent and very specific to how it answers our questions or our interactions. So we're doing this instruction following LLMs. There's actually many papers on this, and I plan on covering one of the main ones that the Stanford team used to create their alpaca model. It teaches the model to behave more like a chatbot, right? That's what we want. We want a human-friendly chatbot. And it's a better user interface for model interaction. So it turned GPT-3 into ChatGPT and increased AI adoption for thousands of researchers from researchers to thousands or millions of people around the world, or billions. So what do you need to do this? You need some existing data that's in the form of question, answer, or instruction following, right? You need some kind of interaction, right? You're trying to do instruction fine-tuning, so instruction following. Well, guess what? You need instructions and examples of outputs from those instructions. So maybe your project or company has already some type of frequently asked questions, FAQs. That's a great way to convert those into training data, fine-tuning data. Maybe you have customer support conversations. You can train those Slack messages. If you have, again, if this is ethical and if this is a responsible way to do, and if this is private and you have everyone's consent to do this, you can use this method too. So what is the data generation process? You can take another way would be, hey George, I have all this documentation about my products. Yes, I can ask my subject matter experts to write me 1,000 Q&A, but it will take me a long time, right? You're basically having a whole data generation pipeline. You can do that. That's of the highest quality. I would say start with that. But another approach would be give it as an input to a private model that you have on your own infrastructure, and give non-Q&A data and ask it, use a prompt template and use an LLM, a privately secure LLM, open source LLM, and ask it to convert it to Q&A type of questions, right? So I might have a README that describes a little bit what my product does. Well, you can interact with it, you can prompt it, meaning, hey, using this README as input, how do I do this? How do I do that? How do I do this? How do I do that? Or you can even ask it, hey, can you generate some simple prompts for me so that a beginner level user would have for my product, and maybe an advanced level user would have for my product. And this is exactly what ChatGPT, the Stanford team did. They used the DaVinci 003 model, which is the one of the models behind ChatGPT 3.5, and they picked a category. You'll see that in the next sessions I will cover, but they pick a category, science, math, arts, history, coding. They picked a specific type of prompts. Okay. I don't know if they even asked ChatGPT to generate the prompts for them. I think they sampled, they created some high quality prompts, and they asked ChatGPT, what is the answer to this prompt? They collected all of that, and they now have 52,000 records of input and output of instruction and answer. And then they fine-tuned the Llama 1 model, 7 billion, with $500, and they have a very high, not highest performing. Again, it's not going to be as high performing as this, but it's 80% there, 70%, 80% there in terms of performance. So it's a really good way to fine-tune it. So fine-tuning can access the model pre-existing knowledge and can also generalize following instructions to other data, not in fine-tuning sets. So if I ask now what is the capital of France, it's not going to give me what is the capital of Albania, let's say, or US. It's going to give me Paris. And if I ask it something that maybe I didn't expose it to, so I didn't expose it to coding data. And let's see, I ask a coding question here, it will actually give me coding answer because the base model itself was trained on coding data. I just gave it the behavior to answer my questions through fine-tuning. Awesome. So the summary here, what is the overview of fine-tuning? It's all about data. So please keep it safe and secure and use it in a responsible and ethical way. This is the only thing that now in the long term will differentiate companies and business models. You do the training, the fine-tuning, similar to training a large language model, and then you do the evaluation. We'll talk a little bit about this, how you do this evaluation, because we're talking about knowledge here. We're talking about text. It's not, confusion matrix in a classification problem, right, or regression problem. It's actually text. So I probably have an ideal output, what I expect. I have the output that my model gave. Somehow I need to compare them, how close they are to each other. In embedding space, how many words are in common, how coherent it is, how friendly it is, how harmless it is, honest, helpful, harmless. Okay, let's look at this template and how we're going to do this with our data here. So I'm going to jump on lab number 3. Okay. Instruction fine-tuning. Yeah. And Let me zoom in a little bit more. So data set from Hugging Face, basic model runner from Lemon Llama, and then from Hugging Face transformers, tokenizer. We're going to see this extensively in this lab. Models and auto tokenizer. So auto tokenizer basically, oh, why is this twice? Okay, that's weird. Is a way that this library identifies the right tokenizer based on the model. And we'll talk about this for a second. Well, we're going to download from Hugging Face this alpaca model. Let's see if I have it here. Okay. So this is the alpaca model here, the alpaca, not the model, the data set that was trained. There's 52K records here, number of rows 52,000. Let's look at one of them. Give 3 tips for staying healthy. Okay, eat a balanced diet, make sure to include plenty of fruits, exercise regularly, and get enough sleep. Okay, and this is in the form of instruction and response. 3 primary colors, structure of an atom, how to reduce air pollution, very important. Describe a time when you had to make a difficult decision. Identify the odd one out. So you see here that I want to show something critical. Many of them don't have an input. Some of them have an input, right? So the instruction is give me 3 tips. There's no input. The output is here are 3 tips. In this case, the instruction is identify the odd one out. We could have included the input in the instruction, but in this case, we left it as an input. Maybe there's some kind of operation we need to do here. And the output is identifying the one that's different. For example, identify why the following fraction is equivalent to 1/4. And here we can give any input we want, right? And here's the output for that specific input. Cool. Something that the model cannot do, render a 3D model of a house. Well, no output. This type of instruction cannot be fulfilled by a GPT model, right? So that's the data set. So let's take a look at it. It's again from Alpaca, from Stanford. Let's look at the first 5 records. And these are the same ones we saw before. Give me 3 tips for staying healthy. So you have the instruction. I want to make sure this is, yep, you have the instruction. Actually, I want to make this as this. Okay. I have my instruction, and then I have my text. And then in the end, I have this instruction answer type of conglomerate merging. Okay, let's see which part we're going to use for air pollution and so forth. Cool. So now what we're going to do is we're going to add our own prefix to our own template. We're going to say below is an instruction that describes a task paired with an input that provides further context if that input is needed or is there. Write a response that appropriately completes the request. So we have our instruction, we have our input, and later on we're going to have the output. This one does not have an input. So below is an instruction that describes a task. There's no input here. Write a response that completes the request. Slide a little bit. Okay, good. Let's hydrate our prompts. Basically, what this means, and Sharon says this in the course, is now we take our training, highly curated, fine-tuned data, and we are going to create. We're going to convert them to this template format. So we want to take them, and we're just basically formatting them where the instruction or the input is there based on if the input is part of the text. Okay, so let's look at one of them. Below is an instruction, describe a task, write a response that appropriately completes the request. That's literally the same prefix for all our prompts because it is hard-coded here. Okay. Zoom out a little bit. There you go. Right, it's literally the same. And then what I can do with this, well, sorry, the instruction is here and the response is here. The response ends with response quotation mark, and then the output is here. I want to make that clear. So input, output. You can save this, you can do something with it, we'll use it for fine training. So that's from Alpaca, the 52,000 case. Let's look at the company specific one from Lemoni here. And sorry, again, this is Alpaca 52,000. Come on, let me scroll down. And then let's take our base model, the 7 billion, tell me how to train a dog. We saw this before, but this is just repetition. Sorry, I forgot to add my API key instruction here. It's okay. But you get the idea. Let me actually I'll copy paste it real quick. That's something that was omitted in this lab. So let me actually get this too. I think Lemoni is already there, so what we need is actually the URL and the key. Oh, this is not defined. Okay. Lemon is not defined. Okay, I thought it was. Oh, Llama was there, not Lemoni. Okay, got it. All right, let's try it again. So as you remember, repetition. Now let's download the chat version of it and instruction fine-tuned. Yep, training a dog is, you can do this in these following ways, and remember it's a journey and compare it to ChatGPT. Cool. Those are the 7 billion parameters, right? Another key concept here is that you don't need billions of parameters to do this. We'll use these models from a company called Blvd, and I'll chat a little bit about Blvd in the end, but think of them as a research community with members around the world, and they've created these great models, these great papers, these great evaluation metrics. So we're gonna take a look at them. Okay, go back. Close this and go back here. And the way we're going to do that is through this. We're going to need two key components. We need our interpreter / tokenizer, right? Think of it as like we need somehow to convey English to computers. Think of them as like an alien race. They don't understand English. So we need our tokenizer, which is our translator. We need to convert everything from English to tokens, bytes, bits and bytes. And the tokenizer is tied to the specific model that we're going to use. So let's say the alien language, I'm going to just say in a very basic analogy is this PTS 70 million. It's a model. I'm just going to call it as a language. I need that translator / tokenizer. So for this model, I need this tokenizer, and I'm going to download this tokenizer from Hugging Face and load it as my model. And then what I'm going to do is define this inference step. This is very, very important. So all I'm doing is I'm taking my text, whatever my prompt is, I'm taking my model. In this case, that's 70 million parameter model, my tokenizer. I can have a limit how big my token input can be, right? I don't want to be too big, or my output, maybe hardware constraints or maybe time constraints. So input can be big. Let's say maybe we're doing a summary of a short sentence, 1,000 tokens. The output can be 100 tokens. So I want my summary to be just 100 tokens. We'll take from tokenizer here, we're going to encode the text. We will have a max length of input tokens, and we're going to return something called input IDs. Now these are tokens, okay? We will move our model to our device. We'll see this soon. If we have a CPU or GPU, how do we do this? So move our model to our device from memory device. From storage, and then we're actually going to generate the output. So we're going to take our input IDs, we're going to move them into our device as well. If it's a CPU or GPU, you actually need to move them. And then what is the output tokens that I have from my model? I need that output length here. And then I have my generated tokens with prompt. Again, these are tokens, alien language, they don't speak, it's not in English. So I need to decode it, I need to translate it back to English. So now from my tokenizer, I need to call this batch decode. I need to give my output of my model, and it will give me my text. And remember, in my text, I have the prompt. That's what I started with. So after my prompt, so length of text, and after that, Python, this means after that will be my answer. So my generated answer will be this. So let's run this utility function here. And let's also, let's see, let me remember here. So we're also using this data set, okay, fine-tuned data set. I guess the point here was that you can use either your own data set or Hugging Face data set. That's fine. And come on. And then we're going to run our inference instance with our test sample here using our model, that 70 million, and the tokenizer, using one of the test questions here. So the prompt is, can Lemon generate technical documentation or user manuals for software projects? This is the expected answer. Okay, this is the encoded version of my input and my output. And this is what my model answers right now without fine tuning. I have a question about the following. How do I get the correct documentation? Answer, I think you need to use the following code. Answer, you can use the following code to get the correct documentation. So as you can see, it kind of knows that this is some kind of coding related question, right? Technical documentation. So it kind of knows from the base model what does a typical question answer looks like, but it doesn't have the details. It just have a skeleton. It really is lacking. So we're going to compare that now with another model that Lamini fine-tuned. I'm just going to show you the end result, so you're excited to see how we're going to do this soon. But this is Lamini docs fine-tuned. Let's see if I have it here. It's fine. I can open the Hugging Face. That's 282 million bytes. So 282 megabytes here of weights. And let's see the same question, right? Takes a few seconds to run, right? It's a large 70 million. I would say small, but again, we're running this on the CPU. So for the same question, yes, Lamina can generate technical documentation, providing a prompt. Additional Lamina can be trained. Additional Lamina. So you see, it's doing an okay job, but then it starts repeating itself. Much better than what we were, but again, not perfect. And here's a cheat sheet. How would you publish your own data set of Hugging Face? So in Solid Library, there are command line login, data sets. You convert it to this data set format, and then you push to Hub. Cool. So that was instruction fine tuning. Let's go back to our slides. And we have a couple more slides and a couple more labs. Okay. So now we're talking about data and specifically tokens and all that. Let's take a closer look. What kind of data do we need, right? You're going to ask me what kind of data we need, what kind of question answers. So here's some general rules, right? So higher quality, and if they are human generated, and we're the highest quality, right? So it needs to be diverse. Don't just ask the same question answers about the same products, the same type of aspects. It needs to be diverse. It needs to be real. Please don't write a script to generate your data, okay? It needs to be real, meaning try to avoid like synthetic data and all that. There might be some value in synthetic generated data and all that, but again, there's value in asking an LLM to generate it for you, but if it's from actual human conversations, that's the highest quality, because we have so much diverse and nuanced ways to communicate. What is worse is lower quality data, the opposite of that, right? Homogeneity, generated, and less data. So the more data, the better, as is the case usually with deep learning. Tokenizing, right? Tokenizing is you saw this encoding and decoding. So fine tuning is found for all. fine is usually 1 token, space tune is 1 token, ing is a very popular token, it gets converted to token 278, space is, space fun, space for, space all, exclamation mark. Then I can take these tokens and decode them back. Fine, now space tune, ing, space is, space fun. Keep in mind, there's always space there. Space is not a token on its own. It's usually part of a prefix of a word or an entire word. There are multiple popular tokenizers. Please use the tokenizer associated with your model, right? It's the interpreter of your alien language, right? If you talk to somebody from another planet, use their language. If they're from a different galaxy, use their their language translator. So how do you prepare your data? Collect instruction response pairs, ask for subject matter experts, maybe convert a large README to Q&A type of questions. You can concatenate the pairs or add a prompt template if applicable. The answer to the question needs to be there. Tokenize, you pad, you truncate if needed, and you split into train and test. Then how do I train it? Woohoo, this is the fun part. It's one of my favorite parts, right? So what's going on here? So we have our data, our model, our base model. We had our training data. The model needs to compute the output. We have the next token. It's literally doing next token prediction. We have the next token as expected from our training data. Somehow we need to calculate the loss. And there are many ways to do this, right? This is text. So you can look at the tokens. If they do exact match, that's a very harsh loss. I don't think you will work with that. You can embed this, right? You can use another traditional NLP methods, or you can use another LM and just embed it, meaning convert my output to an embedding, a collection of floating points, and look at what is expected and see in the embedding space, let's say cosine similarity, how far are these two vectors? So let's say I'm predicting the next word is supposed to be dog, but I'm predicting junk, it's very far. If I'm predicting some type of animal, I'm closer. If I'm predicting a cat, I'm closer. If I'm predicting some type of a dog, I'm closer. If I'm predicting dog, I'm spot on, right? So my loss is larger, smaller, and smaller, and smaller. Then I calculate this loss, and then I need to back propagate this loss function, and the weights need to be updated so that my loss is minimized. So I need to do this back propagation, and I need to update the model weights, all of them, all 70 million, 2 billion, you name it. That's why it's very important to do this on a small parameter model. Some hardware parameters, as you're going to see, there's many of them, learning rate, the scheduler, the optimizer, you name it. And usually the workflow is we have how many epochs we want to do. In this case here, we're going to have 1,000 documents. How many times do we want to go through that? And we're going to go through that in batches, not maybe 1 document at a time, maybe 3 documents at a time, not documents, sorry, maybe 1 record at a time, question answer, maybe 3 records at a time, maybe 20 records at a time. That's 1 batch. We'll give it to our model, we get our outputs, we're going to calculate our loss as a next token prediction, see how far we are. We're going to do our backward propagation. I'm going to do our optimizer step and update our weights. I'm going to keep doing this as long as we have energy and resources and we see our loss decreasing and kind of like stabilizing. Cool. So here's some example. Question is, does Lemon.ai have the ability to understand and generate code for audio processing tasks? Train model, a fine-tuned model would say, yes, Lemon.ai has the ability to understand, generate code. Base model, kind of maybe hallucinate or just pick some questions here of generating code for audio processing. So it looks like, I think you're looking for language that can be used to write audio code. It just took that. It has nothing to do. Probably wasn't even trained on Lemon.ai back in 2023 or 22. And it's just referring you to languages that write audio code like C, C++, Java, Python, and so forth. Is it possible to control the level of detail in the generated output? Okay, here's the training example, and here's a completely different example on the base model, probably on coding. Has nothing to do with our question. Cool. So yeah, let's look at this training notebook. Sorry. And let's close some tabs here. All right, so that was data preparation. This is the training process. And let me close this. Get some more real estate. Okay, cool. So Sharon is showing here how to do this with 3 lines of code using her libraries and her infrastructure, right? That's the value add here. So from Llama import basic run model, what model you want to use? Let's say the 400 million one from L3 instead of 70 million. What documents you want to use, what question answer pairs you have, what is the input key question, what is the output key answer, train, and make this public available if you want. So three lines. We'll have extra lines here for our own purposes here, but you'll see you choose the base model, you load the data, you train it. And then you get a model ID, dashboard, and playground interface. This is if you do it in Lamini. We're going to do this here on PyTorch, okay? So let's just get some information we need here. Data sets, torch, transformers. We're going to train some networks here. Utilities, I'll spend some time on these utilities because I learned a lot going through it. It's basically a wrapper that has a lot of knowledge, as you'll see here. Transformers, we need the tokenizer, and the auto part basically says, based on the model, let me find the right tokenizer for you. You don't have to specify the tokenizer. It's based on the model, you'll find the right one automatically for you. The model I'm going to run, training arguments I'm going to run, and then from Llama, this is all from Hugging Face. This is local. This is from the Llama library. Okay. And again, I'm going to mention that you have 2 ways to provide your input data, either through a local file, not from Hugging Face, or from Hugging Face, just give the Hugging Face path, relative path, Lamini docs, use Hugging Face true. So we're going to use this one. Model name, 70 million. Yes, please. 70 million parameters. Let's keep it small. What are some parameters, configuration parameters we're going to use? The model name, this one, the length of the output, the data set, the Hugging Face, and give us information, verbose true, yeah? So let's get our tokenizer from pre-trained model name from that 70 million here. End of sentence token, that is important to pad our tokens with end of sentence. And we need to split our training data based on the tokenizer into train and test. So I'm going to train our model on the training data set. And as you know, we're going to test it and evaluate it on the test set, which has data that is not contained in the training set. This is very important. Okay. And downloading the data. Train test. Let's load it. The 70 million parameter model. Okay, 160 megabytes in size. And then this is the device part. So depending if we have a CUDA, we have GPUs available. If I have multiple GPUs, I will use as device my CUDA. In this case, you'll see I have a CPU running on the CPU. Let's move my model now to the CPU. And as you'll see with Deeplearning.ai, they have this GPT-NeoX architecture. You can read more about it on their papers. It's a transformer-based architecture with this rotary embedding, as you can see here. Cool. So now define the function to carry out the inference. Okay, we saw this a little bit earlier, but we have our tokenizer. We have model to device. We have our output that's generated from the model, the core model, translated back from tokens to English, and we'll just spit it out. Okay, so try the base model. So we're going to use our base model that is not fine-tuned here, just to see what is the model output and what is the correct output. Okay. Yeah, so let's see. What is the correct one and what is the model one? So the question is this, can Lamini generate? And correct answer from Lamini docs is this. And the model answers is, you guessed it, this one that's kind of lost, right? Okay. Let's train this model for 3 steps. Like you might ask me, whoa, that's nothing. Well, that's nothing. I agree with you. You won't see much, but CPU, right? I only have so much time and resources to do this. And this is again, we want to start do baby steps. Let's save our data into a folder called Lamini docs 3 steps. So any model outputs and model metadata we need to create, let's store it locally in a folder. And let's use this training arguments from utilities, which is basically a training argument wrapper. So I have my learning rate, number of training epochs, only one, number of steps to train, it overrides number of training epochs if it's set. So yeah, I'm only going to do this for 3 records. I'm literally going to feed 3 records out of 1,000 to my model. Later I'm going to feed it 2 epochs or 3 epochs. You know, you're going to see later on 2,000 records instead of just 3 records. For now, we're just going to do 3. Batch size 1 record per batch. The output there that we created here. And other arguments, right? So TQDM, update steps, after how many steps should we save the model? We're not even going to reach this 120. We're just going to do this for 3 steps. Evaluation strategy steps, looping steps, optimizer ADA factor here. Okay, checkpoint, false. And then parameters for early stopping, load base model at the end, true. Metric for base model is evaluation loss, and we want that to go down. So greater is better is false. Did I run this? Nope. Okay, let's run this. And let's get an idea here. What is the size of the operations and the model we're talking about, right? So we're trying to understand here a little bit the base model, the floating point operations. What is how many parameters do we have? How many training arguments do we have? And how many accumulation steps do we have? That's our flops here. And then the memory footprint would be the memory footprint in gigabytes. So 0.3 gigabytes for this 70 million parameter, right? So that's 300 million bytes. So think of it that way, like 4x, 4x from parameters to bytes. And then 2000 gigaflops in terms of operations here. Cool. Then use this wrapper again. It's in utilities, and I'll cover utilities right after this. We have our base model, how many flops, how many steps we're going to train this for, the training arguments. This guy's here. A training data set and a test data set, right? And now we're going to train it. Let's see how long this takes. That's why we're doing this for 3 steps. Sit back, enjoy your cup of tea or coffee, and let this run for a few seconds. Okay, step 1, step 2, step 3, ends. So loss, more or less the same, 3.3, 3.2, 3.4, actually went up. Learning rate might change. And this is the output after 3. So I'm going to save the model in a local directory, save it here. And if you want to look at it, I'll take a look how that looks like. And now let's load it from my saved directory. Let's load it in this auto model for casual LLM. Fine-tuned slightly model. This is our slightly fine-tuned model. Put it to device. And let's ask it, woohoo, the question. Can Lamini generate technical documentation? And the answer is, drum roll. This is the gigaflops and all operations happen. I have a question, I have a question, I have a question, I have a question. Okay, kind of got at least the Lamini specific software development process. I'll give you a bonus on that, right? Other than that, it's just repeating itself. And the target answer is this. Okay, we're actually going to download from Hugging Face. You'll ask me now, 3 is nothing. Go do it like 1,000, 2,000, 3,000, 3 epochs, 4 epochs, 10 epochs, you name it. So let's do one that was trained for 2 epochs. It's already in Hugging Face. The Lamini team, I'll pull it in Hugging Face. I'm going to download that. I'm going to use their tokenizer. I'm going to move that to my device, and I'm going to do the inference for that. Let's use this. Let's prompt this now with the same question, test question. And the answer is Yes, Lemon can generate technical documentation, can be achieved by providing a prompt. We saw this in the beginning, right? By providing a prompt. Okay, by providing a prompt. It's kind of repeating itself, I think, a little bit, right? Additionally, yeah. Okay. When I ran this last time, I think something changed on the back end of Lemon, and this bigger model wasn't available. But before I go there, let me show you the back end here of the few libraries that we created, right? Oh, sorry, the few folders that we created. So we created this Lemon docs 3 steps. And here you'll see the metadata or anything that was created as part of that. So this is the configuration part, right? The architecture, the model, the hidden size, and all that. So again, if you're learning more about transformers, all of this will make more sense to you, especially from a implementation perspective. Okay, let's look at some other ones. Generation config, PyTorch model. Oh, this is a bin file. That probably won't be able to see it. Yeah, it's not UDF8 encoded. And transformer version this, the library from Hugging Face. Cool. So let me go back. I wanted to show you this. Oh, actually, let me finish my notebook and then I'll very tell this. This bigger model name, it's, let's see, it's this one here. I don't think it will run though. Something must have changed on the Lemon side. Yeah, this is from Lemon. So this is a 2.8 billion model. Yeah, it's telling me could not find model name PCI 2.8 billion. Which is a shame because I want to try this one. It's fine. This won't run either, but this should run. Let's explore moderation using small model. Let's try the non-fine-tuned one. This is the basic one, right? What do you think of Mars? The base model, the PCI 70 million. It will probably repeat itself multiple times. And then let's see how, yeah. And let's see how the one that was trained for 2 epochs. But then again, it was trained on our company data. It has nothing to do with Mars. So I guess it will just start repeating itself or say something, keep it relevant. Yeah, keep it relevant to Lemon, right? Because we had some random questions there in our company training data set. And whenever the model kind of figured out that, hey, this has nothing to do with our products or company, and they kind of figured out is whole math and a whole science behind it, it was able to give us this, which is great. I'm pretty sure there was no Mars related questions in the alumni document. This is the alumni document. Let me zoom out. Let me control F, Mars. Nothing. Let me control F, leave. Yeah, there's some liver jokes. No, but there's nothing about Mars here. So to me, that's interesting. Okay. Then let's evaluate this a little bit more. So this bigger model now. Let's take this. Let's use the Lemon. So this is how we're going to do this using Lemon, right? So we saw how we did this here using our own trainer, our own arguments, our own steps, our own inference, device, all this work, right? All these notebooks. So now Sharon and her team developed this product that you can use their library using their API keys. You provide the model you want to use, figures out the tokenizer. You provide the input, output, question, answers. It does the training for you, and you just have to do this. Okay. And I think this didn't run because probably something changed in the backend. Yeah. Oh man, that would be so cool. Maybe I can do this next time using their APIs and actually use the latest version of their APIs instead of the one they have in this notebook. Evaluate this one work and then this will work. But then yeah, no worries. We'll take a look at another one. But yeah, the value proposition here is that with 3 lines you can do this if you have the right API key. It looks like I don't on this notebook. maybe they or something changed. Okay, let me zoom out a little bit, and then let me go to the next and go to our slides. Okay, so evaluation. Okay, this is great, George. But what does this mean? I'm getting some output. How do I know this high quality? Do I have a human? Do I have somebody from my team look at the output and give you a thumbs up, thumbs down, give you a 5-star, give you written feedback, and for 1,000 Q&A prompts, let's say I just want to do one iteration of my entire data set. Let's say I have 1,000 Q&A or answering questions type of data. If I have one evaluator, that poor person has to evaluate 1,000 records. In multiple cases, I want 3 evaluators, right? Maybe my evaluator is also just for not for redundancy, but also for diversity and plurality, right? I want diverse ratings, so maybe I want 3 evaluators evaluating 1,000 records or outputs, 3,000 evaluations. That scales up pretty fast, and it's expensive and hard to scale. So human evaluation, golden standard, right? Human evaluation is the most reliable. Well, of course, because we're trying to replicate human knowledge and human understanding. So human evaluation is the trusted source. The other approach would be some kind of automated test suite where if it's like very technical, if your product is very technical and you have what are the model specifications of my product? Well, you have the exact answer, right? You don't need a human evaluation. You probably have it in your documentation or you can generate it. That could be your test suite. Or maybe you have a very specific fine-tuned test suite, maybe a Python test suite like you do for Python. You have your input and you have your expected output, and the output is very specific. You can do that evaluation using test suites. So good test data is crucial, high quality, accurate, generalized, not seen in training data. So you need test data that is like this. The other one is this ELO rankings, and I was reading a little about this. This started in chess, but basically what it says that is how do you evaluate version 1 of my model is better or worse than my version 2 of my model based on symmetric. And this ELO rank is basically give you an idea that when there is a comparison between 2 models, one has a higher ranking than the other. As of now, but then you evaluate them and this lower ranking actually performs better. This ELO ranking of the higher one will drop by a lot, and this ELO ranking of this lower performing one will increase by a lot. If the higher ranking one wins, she will only, or this model will only increase by a tiny bit or stay the same, and this one will probably decrease by a tiny bit or stay the same. So it's basically a way of ranking that reinforces in the long term true performance. It's a way for you to gauge true ranking and true performance. Okay, so suite of evaluation methods. There are some common LLM benchmarks. You might see them in different papers, Llama paper or the Gemini paper, or model cards, or OpenAI's model cards. Again, this Blvd.ai is really cool community because they've created this benchmarks. They have one called ARC, which is a set of grade school questions, right? So elementary school questions, different topics. Hello Swag is a test of common sense. Again, you can take a look at this. They're really interesting. MLU is probably the most comprehensive one. Is multitask metric covering elementary math, US history, computer science, law, and more. Untrustful Q&A measures the model's ability to reproduce falsehoods commonly found online. So then a typical benchmark might look like model as the first feature here, Llama 2, Free Willy 1, Free Willy 2 using a training model called Orca. We might cover that in the future. I'm still learning about it. And then you have the different benchmarks, so ARC, Hello Swag, MLU, Truthful QA. How does Llama 2 perform? Symmetrics. How does another one perform? How does another model perform? And then maybe you want an average. Maybe you want to take an average or some kind of weighted average, and you get an average of performance for these models. And the other thing is the error analysis. Maybe your model is stuck in a corner of this optimization journey, and maybe it's doing misspelling, maybe it's giving you too long of an output, maybe it's repeating itself. So it's really critical to understand the behavior, understand the error, and collect data or update your data that fix these problems in the data space. Okay, let's look at our last lab here. 6. Okay. So yeah, let's do this here. Let me make this a little bit bigger and hide my zoom controls. Okay. And zoom a little bit. Okay, so actually, sorry, I forgot to give you the utilize. Okay, let me finish this. I promise I'll cover it. Lemon docs, question answers, fine-tuned. What are some evaluation metrics we can use? This is literally the same as we saw before. One is we can strip the spaces and we can see if my model output and what is expected is exactly the same. Well, guess what? That will probably never happen. So again, it's my inference. I want to run my model. So I have my answer and my expected answer. I have my generated answer and my expected answer. Using this stripped exact match, they don't match. What if I keep doing this for 10 records in my test set? Let's see how many of them we get. Evaluate all of them. Still running. Still running. Number of exact matches. Any guesses? Talking about exact matches, right? Come on. Evaluating. Okay, how many are we doing here? 5, 10. Oof. I need a faster GPU or CPU here. Maybe Colab. Maybe TPU. I'm curious how this will perform on TPU. All right, well, long story short, I don't think we'll get any exactly right? So exact matches will be 0. Come on, you can do it. So the question, the answer, the tokens, attention mask labels. Okay. Should have said number equals to 3. All right. So close. Evaluating all of them, and then we have this arc benchmark. This takes a long time to run, so I have a screenshot of this. Okay, how many? Number of exact matches? 0. Wow. Okay. So yeah, predicted answer, target answer, and what we're expecting. Yeah. I'm not going to run this. I'll share the slides of this arc so you can see it, and then I'll show you the utilities page. So if you run this, it will take a long time to run. You'll get a score in the end, arc score 0.31. Interestingly, this is arc, right? So this is about grade school questions. So we fine-tune it on Lemon product, company type of information. Probably there's no grade school type of information there. So I don't expect this to change. It probably went down a little bit because you might have forgotten some common grade school question type of knowledge. I don't know, right? Or it might be very similar. If we were in the, let's say, we're fine-tuning on like law specific or computer science specific information, and that was our fine-tuning data set on, I expect this MMLU to increase a little bit. Not by much, again, by a tiny bit. Again, these are specific benchmarks that measure very specific fields, right? Cool. Okay. So before I actually, yeah, let me cover this and I'll cover the utilities. So practical approach to fine-tuning, some wrapping thoughts here. Figure out your task, collect the data related to your input task, generate the data if you don't have enough data. Fine-tune a small model, please. Less than 1 billion, okay? We saw 70 million, 400 million, 1 billion you have to. Vary the amount of data you give to the model, evaluate your LLM to know what's going well or not. And you can have your own custom metric, right? Maybe probably this MMLU and ARC are not relative to you. Maybe you need some subject matter experts feedback as part of your evaluation, or those test suites type of evaluations. Collect more data to improve, increase task complexity. Maybe instead of asking simple prompts, you're asking now more complicated prompts, right? And then increase the model size for performance. And then this is a slide here that if you use an AWS instance now, P3 2x large, it has 1 GPU, V100, has 16 gigabytes of GPU RAM. It can only host a model that has 7 billion parameters. And in terms of data or fine tuning, I cannot fine tune it more than a larger data set, more than 1 billion tokens, right? So data is tokens, and I can only basically fine tune it on 1 billion tokens. If I go to 64 GB, the same, 128 GB, the same. If I go to 256 GB, 8 V100s cards now. Okay, now I can double the model size. I can go to 14 billion parameter model, but my data doesn't, I mean, it doubles, but don't expect too much. It's still 2 billion tokens. 320, 18 billion, 2.5 billion, and then this 640 gigabytes of memory, 32 billion parameter. Not even close to the GPT world, right? Which is 170 billion parameters, or even half a trillion parameters. And the model training size is 5 billion. Yeah, so depending on the task, right? If you complexity, more tokens out is harder. So reading is easy, right? So if you're trying to summarize, I'm not generating that much. I'm ingesting a lot, but I'm not summarizing a lot. So I'm not doing inference on a lot. I'm not generating a lot. So that's easier. You probably need a smaller model here, right? Writing, well, guess what? You're going to expand. You need a larger model. Also combining tasks. Maybe, I don't know, maybe you need both, or maybe you need multiple summaries or summary, and identify key stakeholders, and identify next steps, and identify what was the tone, and identify when is the next meeting, and. The moment you have multiple complex tasks, this smaller model is gonna give out, right? So you need probably a medium model or a large model. And these are relative terms. Again, try it, right? Try with a small one, few hundred million, or few million, few hundred million, few billion. You can more than that, few hundred billion, good to you. I don't think it's feasible, but yeah. And then yeah, if you want an agent to do multiple, or an assistant to do multiple things, then you need a larger model. Cool. Before I talk about this, let me go back and talk about utilities. Hey, so this is a helpful utility function here again. So we use the transformers, the model name, initialize and config and all that. I want to show you something that I found interesting. Logging, okay, tokenize the split data, that is here. My dataset path, load dataset, okay, train and test. Okay, so it's using this load dataset, which I've overloaded here, and you can see it's loading the data, and of token, it's fine. Based on the data, it's mapping my tokenized function, and we'll see what that looks like. It's batching it, and it's creating a test split, and test split, and it's giving it back. So this tokenized function takes a tokenizer and a max length as optional, and it concatenates my my input and output. Trying to see, because this is probably a global variable here. Yeah, it's actually in. Let's see where's my text and my input here. Okay, so trying to find this text here, which comes from examples, which comes from, that's what I'm trying to understand a little bit better here. Oh, it comes from, because I called it as a mapping function, right? So it comes from this fine-tuning dataset dot map. So it already has that as an input. That's where it comes from. So NumPy array, I tokenize it, the input. This is again the concatenation of question and answer, NumPy array, panning, and then I need to calculate the length of it and probably trim it if needed. And then I need to tokenize it, and then I'll need to give you the tokens as an output. And again, these are tokens, and I return this function actually as get tokenized function output. Then I load the model, tokenize your model. I need to see if I have a GPU or CPU. I need to move it to the device and load the path and return the data. And this is the trainer class that has the model, the flops, the steps. We saw that. Call it parent class. And then let's look at the training steps, right? This was interesting to me. So I need to prepare my inputs. I need to compute my loss based on my model and inputs. And again, the inputs have the instruction and the answer baked into them. And when you're doing next word prediction here, so basically there's no labels, right? When I was looking at this first, like, where's my label? Where's my answer? But it's actually baked into the input. So we're fine-tuning it in the sense that we are literally doing next token prediction at the record level. So we're taking a record, predict, including the prompt. We're taking the record, predict, including the prompt and the wrapper, any wrapper that we might have put in front of it, right? This is a sample question. Please give me an answer. Calculating the loss on this next token prediction. We're aggregating it, and then we're doing a backward propagation and updating the weights. Logging. Cool. So I wanted you to see that. And then if you go here in the documentation for transformers, you'll see here, yeah, this is what I was looking at the loss. Your model can compute the loss if labels argument is provided and the loss returned as the first element. This is generic because trainer can take any model as an input, right? The model can be anything, and arguments and all that. And I was looking at the code for it, so this trainer.py, how the loss is computed. And we have our model, our inputs, and we run it through our model. And if we don't have labels, then we might just, if we do have labels, if label is not none, then I take my my loss would be the output of my model and the labels as I expect them. And I have this label smoother that calculates my loss, how far they are based on my loss function. Otherwise, if I don't have a label, I'll just give whatever output the model gave me as a loss. So I just wanted to take a closer look here. Yeah, this some other things. Let's go back if I have anything else here before I go to other resources. Oh yeah, let's go back to the slides and a few more slides left. So as you saw, you took 3 steps. It took a while, like a few seconds to train. A few epochs is going to take way more. What are some parameter efficient fine tuning you can do? Meaning, if your model is, let's say, 2 billion parameters, it's going to take a long time to train, right? We saw the slide here and the cost. So, well, maybe you don't need to update all the weights, right? Maybe you can do some kind of smart updates. And one of them is this low rank adaptation of LLMs where you're doing these matrix multiplications. Well, in linear algebra, you can represent a matrix or a representation space by multiple base vectors, right? Orthonormal, orthogonal bases. Think of it like single variable decomposition in linear algebra, right? You can represent an image or a data set with 1, 2, 3, 4 base vectors. And the more you have, the better. But the amount of information that's contained in these base vectors is in decreasing order. So the first one has the highest information, and less and less and less. But the collection of them gives you a pretty okay, a pretty well defined presentation. It's going to be 100% representation, right? Not all information will be there, but 80%, 70%, 60%, again, depending on how many of these values you keep, you're going to have. So this low rank adaptation tries to looks at these huge matrices that we need to multiply in vectors and tries to represent them in a more sparse parameter space. So it's low rank. For GPT-3, for example, we had 10,000 less parameters and less GPU memory, which is critical, right? 3x less. So instead of 1 billion, you need like 300 million RAM bytes. Slightly below accuracy to fine tuning, but same inference latency. And the way you do this, you have these pre-trained weights, freeze main weights, and then you do this LoRa low rank adaptation matrix multiplication. And you just update these new weights. And then at inference, you combine them both. And you can do this to adapt to new tasks. So LoRa is one of these reparameterization-based methods, right? There's some other ones. You have selective, additive, adapters, soft prompts. There's a whole paper that covers them. And I'm hoping in some upcoming sessions we can check out some of this. Cool. That was a lot of information. Questions, comments, feedback, feel free to leave them on our YouTube channel here or Meetup. But yeah, as our friend Albert says, where there's a way, right? So yeah, thank you. I have a couple more bonus slides. I'd love to run them quickly by you. Again, join us and Deep Learning Adventures. There's a Slack invitation. Lamini, check out their Hugging Face as well as their company, right? So prompt tuning, you have a data pipeline, a base model. You change the prompt, you prompt tune it, you get an answer. But here you have a data pipeline, you select the base model, you fine tune it, you evaluate it, you sense it, you prompt tune it if you want as well. And then you keep doing this and then you deploy it, you have a better solution. Yeah, Hugging Face, the meta as well, the library is there. Hugging Face library from Meta Llama. The Lamini docs, as you've seen this, I added a slide on it. The Alpaca one, below is an instruction that describes the task. Utilities, I covered that a little bit. Blvd, their community, as well as their paper, right? How public is the model or the data? They have a comparison here, their models, which are both open in terms of models and data, how they're trained, right? You want to foster innovation, you want to keep sharing and in a responsible way how we trained models, both from a data and both from a model perspective. The Hugging Face documentation, GPT NewX, if you want to learn more about that. And then there's this language evaluation harness. We use this a little bit for ARC. But this again is from Blvd.ai and how it was trained. So simple instruction, self-instruct, data set size, and different teachers that were used for this type of instruction tuning. So basically we use a larger teacher model to create our data. And this is how Alpaca was created, and some other ones, including Vicuna, Dolly, WizardLM, and Orca. Curious to learn more about them. I literally today learned pretty much a lot about Alpaca, and I'm planning to do a session on it. Speaking of Alpaca, this headline here from Stanford Daily: how Stanford researchers attempted to make a new ChatGPT with less than $600 is there. That drew my attention. You use this paper, so maybe I cover this paper first, self-instruct. Then we cover the Alpaca, and this is the Alpaca data set and Alpaca model as well. You can find it, both of them on GitHub. Cool. So let's see. What else did I want to cover? So some courses I took at Stanford, Lamini. So yeah, Hugging Face from Alpaca. This is the paper we will cover. Blvd.ai, PTS 70 million. This is the article. You can even run out GPT on Raspberry Pi here. And yeah, I highly recommend reading this announcement. Again, it was from a year ago, on March 2023, from Stanford. It's based on Llama 1, Alpaca 7 billion. GitHub is here, how they trained it. I'll cover this extensively in a new session. Some of its limitations, what are they releasing, and acknowledgements and future direction. But yeah, the model is here. They disabled the demo for specific reasons and explain them why, but other than that, you can take a look at the data, alpaca data.json. We saw it a little bit during our course, and you saw this, right? Give me 3 tips for staying healthy: input none, output, diet, exercise, and sleep. 3 primary colors, structure of an atom, you name it, you name it, you name it. 52,000 of them using GPT, right? So the high level, use GPT to create high quality input output pairs. You take Meta Llama 1 7 billion, you fine tune it, you get supervised fine tuning here, and you get Alpaca 7 billion. That is so cool. Yeah, I have a whole collection of resources I'm going to use for my next session here. Okay, so more is coming. Okay, I think that's it on slides. Go back to our meetup. And yeah, next session, maybe when I'm back from my Euro trip, next week, next month, I'll do a session on Alpaca and the self-instruct paper. I learned a lot there. Okay, with that said, thank you everyone for joining us. I hope you found this useful. This was a little bit longer session, and I appreciate your feedback, and looking forward to growing and learning with you. Have a great rest of your day. Let me stop the recording.